Tung tung. So here we are on final review day 3. And we are starting on the practice final exam number 2. And if you thought the last one was hard, this one's just as hard, so that's why we're here, and hopefully you're here to learn. One more testing wisdom that I like to add. Put that in quotes because I'm not actually that wise. If you start a problem and run into a dead end, and by that I mean you're stuck for maybe longer than 2 minutes. Longer than a few minutes. Don't keep thinking hard about where you are. Instead, start over. It's more than likely that you made a mistake early on. But I want to add to that, so I'm going to circle a few things here actually. So if you run into a dead end, I'm going to say start over. That's because you likely made a mistake, but here's another important thing, but turn in your work for both. Well, I should say for all. For every time. For every attempt. You likely get more partial credit. So this is a really good thing. This is something that I did all the time in math exams. This is very special with math exams, I think, because partial credit is huge in math exams, and running into dead ends is huge in math exams. Like you don't start some philosophy exam where you're supposed to analyze what a philosopher had said and run into a dead end. This is a very specific thing to math exams, but it's good to learn it and good to be used to it. So turn in your work for every attempt, and also if you run into a dead end, start over, because you're gonna do better off maybe trying it a different way. So start over, and I should say, and try something new. That's a big point here too. So you start over, try something new. If you run into a dead end, start over, try something new. If you're trying U substitution, maybe your choice of U was wrong. If you were trying integration by parts, maybe your choice of U and V was wrong, etc. You're maybe just using the wrong rules. So here's what I'll say as well. Think about that rules list I give at the top as a toolbox, and if you try one tool for the job, it's not working. Go back to the toolbox and grab something else. Right? That's the same thing you would do if you literally had a toolbox and something wasn't working. Maybe you grabbed the wrong size wrench or something like that. So go back and grab something else. Okay, so there's my testing wisdom for today. I hope it makes sense. This is something that I've done all the time. And it was really, this is really a necessity in math when you get to really high level math, because there are some things where you just have no idea what you're doing for the first few minutes, and so you just continue to try new things until one of them works. And you can normally tell when one of them starts to work, and that's why, it just feels like everything is falling into place then. And then, you kind of have the right tool for the job and you work with that. Okay, let's actually work with practice final exam 2. And of course, just like before, we're going to go through the first 4 problems. Problem 1. Problem 1 mimics practice final exam 1 very similarly. It has question 1 here. Wants you to find dx of h of g of x squared. And it gives you the answer, but just like before, don't look at the answer. So I would advise you not to look at the answer. Until you try the problem at least once. That's just going to give you maybe a better idea of how I want to see the answers phrased when you guys are turning stuff into me. Don't use the answer, just compare your answer to the answer. All right, so we want to do this. We want to phrase this in terms of h prime and g prime, just like practice final 1. And once again, this is trying to test our derivative rules. So what rules are we going to need here? I don't see, there's certainly no fraction, so no quotient. The big question here is there a product? And this is something that I think a lot of students in your situations are kind of messing up. The answer is no. And the reason being is there's a slight difference in notation when functions are multiplied versus composed. And of course, multiplied functions would be the product rule. And composed functions is the chain rule. So this slight difference in notation, and I hope you'll get used to this. Fx, gx, this is multiplied. Notice 2 x's. f of g of x. This is composed. And you'll notice one function is like in some sense inside the other. I know a lot of you are probably like saying, of course we see this, Evan, but other ones of you, I know this is something in the past that like people have gotten confused with. So one function is inside the other. Also notice, I should say also, only one x. So there are two x's in the top version. There's only one x in the bottom version. So that should tip you off to composition versus multiplication as well. So just get used to this notation. Even though we've been using it the whole semester, just get used to it. And that'll help you out a lot here on these sorts of problems. So you'll notice here we only have one x. So this is composition. And with composition comes the chain rule. Okay, what's going on with that 2 out the back? Well, I'm going to rewrite this actually like this. d dx, so many parentheses here, but I've said it once and I'll say it again. An excess of parentheses is never a bad thing. So more parentheses is more chain rule. Basically, you should think, in some sense, when you see parentheses, apply the chain rule. And if there's a term like a squared or something that could be put around parentheses, always do that first, and then it becomes a little bit more apparent that you're using the chain rule. So let's do this. Let's do the chain rule on it. Chain rule number 1 here would say derivative of the outside, leave the inside the same, multiply by the derivative of the inside. So here's how I would write it. H of g of x again. And then I put a prime out on that side. So this is derivative of outside, leave inside the same. And then this is multiply by derivative of the inside. So there's one more step here because we don't really have it in terms of h prime and g prime yet. So we're going to take this out to one more step. The first term gets left the same. But the second term, this is yet another chain rule. Do this in blue. So we're gonna take the derivative of the outside. In this case, the far outside parentheses aren't really saying anything. That's just the placeholder for the prime. The outside function is h. I think everybody can see that. Between h and g, which one is outside? Well, h is outside. So the derivative of the outside is h prime g of x multiplied by the derivative of the inside is g prime of x. So this is now derivative of the outside multiply by the derivative of the inside. And this happens to be, this is the answer the exam gives. Okay. So there's question 2 here. It's just like on the first exam where there's actually 2 questions here. So question 2 is looking for, man, I was mean on this one. It's good that we're covering this, but I was really mean. DDN, okay, so that's the first special part, is I've put a DDN here. And then now, the function we're trying to take a derivative of is n to the x power plus x to the n power. And man, I was mean here. So let's just talk about a few things right off the bat. The dn on the bottom means we treat n as the variable. And x as just a number. So I'm trying to get you guys to feel better about using any letter for any variable. That's the way that mathematicians have to use it eventually. And that's that any letter can be any variable. And there's nothing special about x sometimes. There's nothing special about y sometimes. We have things that we do commonly, but they don't always have to be that way. So here we're treating n as the variable and x as just a number. So that means here, let's just split this off as we actually try to do this. We'll do this in 2 pieces. Oops. See, I'm already having problems getting used to this n in the DDN. So let's do this in 2 pieces. This first piece here, I'm going to pull it down. Let's do it in blue. This will actually be the power rule. That is ddn of n to the x equals x n to the x minus 1. And this is like our power rule business. Question of why. Since there's nothing special about the variable n, nothing special about the variable x, let's switch all n's and x's around and see what that looks like. So that would be the n and the x get switched. And now it looks exactly like our power rule. This would be n x to the n minus 1. Then we can switch all of them back. And we get exactly what I wrote above. I'll just draw an arrow there. Switch all of them back to get that. So this is just a theory. Behind why, if it makes sense without it, don't worry about it. What I'm trying to say is that n's and x's are completely arbitrary. They can end up wherever we want. What the power rule cares about, the power rule cares that this letter in the bottom there and that letter in the base of the exponent here. So the base there and the denominator there, those are the same letter. That's what the power rule cares about. and then it just takes whatever in the exponent and moves it up. Now we have to handle this other term. So let's handle this term, dn x to the n. And now this time will not be the power rule. But rather a version of well, let's write it this way, dy e to the ay equals a e to the ay. It'll be a version of that. Now you notice I've used yet more variables here, but we'll see why I wanted to write it that way. So it'll be a version of this identity. This is just the chain rule for exponential for e to whatever. Since my variable in the bottom is n, right? So that's what I'm trying to say here, is that that variable n is the same as that exponent n. The piece in the denominator is the same as the exponent. Piece in the denominator is the same as the exponent. How do I write? Can I write x as e to something? And the answer is yes. You should all be telling me e to the natural log of x. So x and e to the natural log of x are the same thing. So really, by exponent rules, x to the n equals e to the log x times n. I think everybody can agree with that. It looks weird, but everyone can agree with it. Hence our derivative here e to the natural log of x times n, and now this is what references that thing I used earlier, using so many colors here, yellow. We're going to bring them together. So I'm going to use this identity. If what's in the bottom agrees with what's in the exponent, then I get a e to the ay. So the bottom n agrees with the exponent there. Then all I get with the chain rule is I'm going to get, I wanted this instead. What I'm going to get is natural log x e to the natural log x times n. Or in other words, this was still x to the n. So this is actually natural log of x times x to the n. Really crazy stuff I gave you guys here, but I want to give you basically the toughest problems I can think of on all these practice exams, so that when you come to the actual final exam, you feel like, wow, this was a lot easier than those practice exams. Hopefully that's the way it feels. But I'm going to circle this, and I'm going to circle this, and then if we look at what we were trying to get, those two pieces. So ddn n to the x plus x to the n is the first one up there, which we saw was the power rule, plus the second one here. And this is the answer the exam gives. Crazy problems. So yeah, that's a really good problem. You might see something very similar to that on the final. I haven't written it yet, but I really like that problem, so I might end up using something like that. Anyway, let's move on to problem 2. Problem 2. My computer just died, so it's going to take me a little while to find it. Problem 2 says, as before, this is an integral problem. Q1. Negative integral natural log absolute value 1 over x dx. So, is there any way we can help ourselves out before starting the problem? This is something I'm going to say time and time again. Simplify the function before trying to integrate. So we're going to simplify before we try to integrate. If we can, right? In certain cases, maybe I'm giving it to you in a simple form, but in this case, no. So simplify before we try to integrate. Can I do that? Yeah, log rules. I mean, there are a couple good ideas for how to simplify things. So the first one, we're going to do log rules. So, well, I'm going to write this first as x to the minus 1 because it's always beneficial to write denominators as negative powers. And then once I do that, my log rules kick in, and they say this pops out front. So log rules, I get negative natural log x dx, and of course 2 negative signs. This is just the integral natural log of x dx. And how do we integrate this? We covered this in a lecture not that long ago. Hopefully you remember. The answer is integration by parts. So integration by parts, we follow priorities. So priorities, u equals, the first priority is natural log of x if it exists. And so it does exist, so then dv equals everything else. And so in this case, it's dx. So in our case, dv equals dx, u equals natural log of x. So that gives us that du equals 1 over x and v equals x. Right, this is what we're going to be using, natural logs, or integration by parts style. And so if we're getting uv minus integral v du, then we get, I suppose I technically forgot my dx here. This is equal to x natural log x minus the integral. Well, what is v du? This is x 1 over x dx. So this is just x natural log absolute value x minus integral dx. So that's x natural log x minus x plus c. And this is the answer that the exam gives. As on exam 1, there is a second question to problem 2. It's looking for the integral of f prime x e to the a fx dx. So once again, I like to get you guys to think about these integrals in an abstract sense. We're now wondering maybe what is the best integration technique to use. So I should say which integration technique should I use? We have two choices. We have U sub, or we have integration by parts. So integration by parts, what you want to think about, when do we use each one? We use U sub when we can find a function and its derivative in the integral. We use integration by parts when we have two distinct functions multiplied together. That's how you want to think about these. So if I want to use U sub, I want to find a function and its derivative inside the integral. Integration by parts, I want to have two distinct functions multiplied together. So then the question here is which case more closely represents what we have. Great question. Do I have a function and its derivative in the integral? Or do I have two distinct functions multiplied together? Well, I certainly have two functions multiplied together. But this word, when I say distinct, what I mean by this, distinct, is they're not related by a derivative. Because if they were related by a derivative, that's like exactly what a function and its derivative in the integral would be. So in this case, I'm going to do U sub because I have a function f of x. It's inside my integral. I have its derivative f prime of x. So I'm going to say that here. Since both f of x and f prime of x are in the integral, I'm going to use U sub. So I'm looking for both a function and its derivative. There you go. Turns out, when you do this for U sub, then f prime of x better always be du or something close to du. That's like how du works. But let's just follow. What should u be? We're going to follow priorities. So priority number 1, natural log of x, if it exists. It does not exist. Priority number 2, denominator, if it exists. It does not exist. Priority number 3, exponent of e, if it exists. And I think everybody here is saying that yes, the exponent of e exists in this problem. Okay. So, oops, all the way to the top, yeah. There we go. So u is going to be the exponent of e, which in this case is a f of x. That makes du a f prime of x dx. But this is not completely in the integral. f prime of x dx is instead. So we're just going to divide both sides by a. If we divide both sides by a, then what do we end up with? Du over a equals f prime of x dx. And now that's exactly what we're looking for in the integral. So with these choices, f prime of x e to the a f of x dx, I'm going to make sure that we know where our pieces are. So that actually goes with this piece here. And then I'll do with this other one in blue. That is exactly u. So there you go. Plug these terms in. We get e to the u du over a, also known as 1 over a, integral e to the u du, and that's a really easy integral for all of us. 1 over a e to the u plus c, which is 1 over a e to the a f x plus c. And this is the answer the exam gives. So there you go. There's problem 2 on the exam. And once again, these first 2 problems take a long time, so maybe don't start with them. It's up to you if you want to, if you think you'll have enough time. I'm certainly giving you more time than on the last midterm, so you will likely have more time on this one. You can certainly start with them if you want, but it could take a little bit more time. All right, let's do problem 3. We have a squared plus b squared equals 2ab. I asked the question, what is, let's put q here, what is db over dA? Great question. So this is, again, testing implicit differentiation. And so we'll just recall our steps. Step 1 is take d of both sides. Really take a derivative of both sides, but the d has some special properties that you want to remember. Step 2 is divide by the piece in the denominator. Right, so in this case, dA is the one in the denominator. I'll just circle that here. So it's dA here. Step 3 is bring all terms with what we want to one side. And all other terms to the other side. And step 4 is factor out the term we want and divide by the rest. Let's try to make this work here. I'm going to mention something right now. When I say take d of both sides, don't forget all derivative rules. In this case, product rule. So in this case, we need to use the product rule. We don't want to forget that. I mean, we have chain rules as well, but I feel like chain rule is a bit easier to remember. So let's just follow our steps. I'm going to give a dotted line to separate that part off. Okay, so step 1, let's take d of both sides. So d of a squared plus b squared, and d of 2ab. On this side, it's really d of a squared plus d of b squared. This is really 2d of ab. Okay. So, just going to mention this now so we don't accidentally get it wrong. This is a product rule, since it's a product of variables. AKA the variables are multiplied together. And over here, these are both chain rules. So let's see if we can manage to do both of those correctly. So what is d of a squared is going to give me 2a. And the special thing here is with implicit, if you start with a d and of a variable, you better end with the d of that variable. 2b db. The db tells you which variable did you take a derivative of. dA says which variable did I take a derivative of. So these tell you which variable I took a derivative of. So that's why they have to stick around. On the other side, then, I get 2 dA times b plus a times db. This is exactly the product rule. So if you want to compare it to the product rule, fg prime equals f prime g plus fg prime. Right? So it looks the exact same. The first one had a derivative on it, left the second one the same. Then you leave the first one the same, second one has a derivative on it. So that's what's going on here. I'm just going to rewrite this now to make it a little bit prettier. 2a dA plus 2b db equals, really this is 2b dA plus 2a db. So this was actually step 1 up to now. Step 2, I'm going to divide by dA. So if I divide every term by dA, then what do I get? I get 2a. dA over dA is just 1. Plus 2b dB dA equals 2b dA dA is just 1. And then 2a dB over dA. Great. So first step is always the hardest step here. Step 3, bring all dB dA terms to the left. So I'm going to keep the one term with the dB dA on the left and bring the other one over. So I get 2b dB dA minus 2a dB dA equals 2b minus 2a. So I'll just basically what am I doing? So up here I'm subtracting this 2a, and then I'm subtracting 2a dB dA, really from both sides, right? So there's a negative 2a over here, and then there's a negative 2a dB dA over there. So that's what I'm doing to get to where I got. And then step 4, factor out what I want. Divide by the rest. So I'm factoring out dB dA over here, and I'm left with 2b minus 2a. That equals 2b minus 2a. So if I divide by the rest, I'm dividing by 2b minus 2a, I'm dividing by 2b minus 2a, all of a sudden, everything is equal to 1. This won't always be the case. I'm giving you guys like very strange problems right now, but it's equal to 1. And this is the answer the exam gives. So there you go. But once again, I could have saved a lot of time. A lot of time by simplifying right away. How? Well, what did I write? I wrote a squared plus b squared equals 2ab, but that is actually equivalent a squared minus 2ab plus b squared equals 0, which is equivalent to, double arrow means equivalent to, by the way, equivalent to a minus b squared equals 0. Of course, that's equivalent to a minus b equals 0. And of course, that is equivalent to a equals b. So db over dA equals 1. Just the derivative of both sides with respect to a is 1, of course. Same answer. You can't always simplify these. Just so happens the first 2 days have been able to be simplified. So it's just been a coincidence for these 2 days. Right, for these first 2 practice finals. So, I mean, I would advise you to still do the standard version of implicit differentiation, unless you're super confident you can simplify it. All right, let's do problem 4 and then we can be done for today. Problem 4, I'm really proud of this one. I'm sure you guys will be too. All right, and it's a tricky one. I'm sometimes pretty mean. Problem 4 says you have vital information on the coronavirus that needs to be relayed to Dr. Fauci ASAP. To relay the information, you must physically reach the radio tower. You are riding your dirt bike at 20 meters per second on the road which passes 40 meters from the radio tower at its closest point, P. You are able to ride your dirt bike at 12 meters per second once you turn off the road. You are currently 1,000 meters away from P. How far away from P must you turn off the road to minimize the amount of time it takes you to get to the radio tower? Holy crap, that was a ginormous paragraph of words. So we really need to dissect this. The most important thing to dissect is that and I've emphasized this in the final, is that I use the word minimize. Minimize the amount of time. So that there means optimization problem. And time here means we need a function for time. Not a function of time, a function for time. So I'm going to call this, call it t of x. Capital T of x for now. In an optimization problem, you guys better not forget this. You need to take a derivative, set it equal to 0, solve for the variable. Okay, most of your points are going to come from that. I'm going to write that down again. This is a good test-taking tip. Most of the points I give on these problems come from this. So do it. All right. I imagine you have the final exam open next to you so you can compare with the picture I'm about to draw, since it's an entire paragraph. And we are all indeed the secret agent with vital information on the coronavirus. So we have a radio tower. I'm going to draw this picture. This is as seen from above. Radio tower. This is my radio tower. And it is 40 meters. 40 meters from a road. This is the road. And this is the point P. So that's point P right there. It says you are currently 1,000 meters away. So here we are right now. It's 1,000 meters. Us riding our dirt bike. Something like that. So we're riding our dirt bike over here. 40 meters away. 1,000 meters away. Extend these lines for us. So we're 1,000 meters away, and we can ride at 20 meters per second on the road. But at some point in time, we have to turn off the road. And we can turn off point, call this the turn off point. And after we turn off the road here, that's a right angle, by the way. After we turn off the road, we can ride at 12 meters per second. And so I want to decide where this point should be. The whole point in the question is, where should this point be? So do I drive all the way to point P and turn right and then hit my radio tower? Or do I start right away aiming for the radio tower? Or do I do something in the middle? And so I'm going to give this distance, the distance from the point P, I'm going to give this, to call this distance X. So the distance between my point that I turn off the road and the point P, I'm going to call X. So what do I need to know here? Well, I need to find this function t of x that calculates the amount of time I need, or the amount of time it takes to get to the radio tower. So let's see if we can manage this. T of x, well, if I'm at 1,000 meters away from P right now, and I've called the distance between P and the point where I turn off X, then this is actually going to be 1,000 minus X. So the time it takes me to travel 1,000 minus X meters, I'm just going to write that out. -1,000 x meters plus the amount of time it takes to travel that diagonal. The length of the diagonal. Okay. Also known as the hypotenuse for all you fancy people. All right, so we need to know this. Need to know this. And I said time and time again, let's do it in red. I said time and time again in these optimization problems, if a triangle shows up, you use the Pythagorean theorem. Pythagorean theorem. Right, this is that a squared plus b squared equals c squared for right triangles. And so yeah, we have a right triangle here, and we can use a squared plus b squared equals c squared. So let's call the hypotenuse, the diagonal, let's call it d for distance. So d squared, or diagonal squared, equals, what are my other two side lengths? 40 is one side length, and x is my other side length. So 40 squared plus x squared. or rather d equals the square root of 40 squared plus x squared. So the length of the diagonal that is in my t of x equation is the square root of 40 squared minus x squared. So time, you'll notice, you guys are hating me right now. Okay, the time it takes to travel some distance, this is going to be distance over velocity, right? Distance divided by velocity is the amount of time, plus distance over velocity, and this is really the second distance, the first distance and the second distance in both of these cases, right? So the first one was my 1,000 minus x meters, and the second one is this crazy nonsense up here. So let's make this one blue. 1,000 minus x meters. Make that blue here. And then let's make this piece green. So those are my distances, and my velocities are going to come from the equation. So velocity 1 is going to be, this comes from the problem. It says 20 meters per second. And then velocity 2 also comes from the problem. It says this is 12 meters per second. And so I have t of x equals 1,000 minus x divided by 20 plus the square root of 40 squared minus plus x squared divided by 12. Let's make my life a little bit easier. Call this 1,000 divided by 20 ends up being 50. So 50 minus x divided by 20 plus, let's put everything inside the square root. So this is 1,600 divided by 144 plus x squared divided by 144 to 1/2 power. And now my life can get easy-ish. So now that I have this function, I have a function for what I want to optimize. I can take a derivative. Set it equal to 0. And solve for x. So let's do it. T prime of x. Well, 50, derivative of 50 is just 0. Derivative of x over 20 is just -1 divided by 20. And then the tricky part comes here. So this is going to be this last piece. If I'm taking a derivative here, that's a chain rule problem. It's not impossible. It's not too hard, but it's just a chain rule problem. So the 1/2 comes out front. Keep everything on the inside the same. The derivative of a 1/2 as a power gives me a -1/2. I think everybody, if you think about it long enough, can agree with me on that. So this is derivative of outside, leave the inside the same. And then we have this piece multiplied by the derivative of the inside. What's inside? Well, 1,600 over 144 is just a number, so that goes to 0. And x squared over 144 becomes 2x over 144. And so this is the multiplied by the derivative of the inside part. There you go. The 2's cancel in the second part. But let's just rewrite this out. So this is negative 1 over 20. And then it's really plus x over 144, 1600 over 144, plus x squared over 144 to the negative 1/2 power equals 0. We should try to solve this out. Let's try to do it. So if that equals 0, set it equals 0, solve for x. We're going to add 120 to both sides. X over 144, 1600 divided by 144 plus x squared over 144, negative 1/2 equals 1 over 20. I'm going to multiply both sides by 144. Minus 1/2 here is 144 divided by 20. 144 divided by 20, this can be divided by 4. You get 36 over 5. And then we're going to square both sides. So if I square both sides, I get x squared, 1600 over 144, plus x squared over 144 equals 36 squared over 5 squared. This was to negative 1, so then I can actually, that's basically like a denominator. So multiply both sides by it. Right, this would just be like pulling something out of the denominator to the other side. I get x squared equals 36 squared over 5 squared times 1600 over 144 plus x squared over 144. And this is a point at which it would be a little bit helpful to have a calculator around. So this is really x squared over there. There's really a 12 squared inside of 36 squared, and so that's going to cancel with 144. So I really end up with 3 squared. 1600 times 1600 divided by 5 squared, plus again the same thing. So this is 3 squared over 5 squared x squared. And now I can pull the x squared over to both sides and the other term back. Oh, this whole time I missed no, I did everything right. Yes, I did everything right. So I pull this term over and pull that over to the other side. So if I pull that over to the left side, I really get 1 minus 9 over 25 x squared equals 3 squared, that's really 40 squared, right, over 5 squared. And over here, this is actually 16 over 25 x squared equals 3 squared times 40 squared over 5 squared. What is 16 over 25? That's actually 4 squared over 5 squared. You guys love how many squareds I put in this problem. 3 squared, 40 squared, 5 squared. Take the square root of everything. We get 4/5. X equals 3 times 40 over 5. And you guys are just hating me right now that the numbers even work out, because I actually put a lot of effort into making sure the numbers work out. So I'm multiplying both sides by 5/4 to get 4 times 5 over here. 5's cancel. The 4's kind of cancel. We get 3 times 10 equals 30. Yep, so x equals 30. 30 meters. This is the answer the problem gives. You guys are probably so mad at me about that. It's going to be a lot easier than that on the actual final. I just wanted to see how far I could push things for you guys and see if you can see what sorts of fun problems you can solve. This is actually a really fun problem. And, you know, if you were a secret agent who had to dirt bike across to a radio tower, you would know exactly where you should pull off to minimize the amount of time it takes you to get there. Anyway, that's all I have. I hope you guys are having fun studying, and if not, just have as much fun as you can, I guess. See you tomorrow. Bye.